Yeah, they are very small, so they will hardly take one or two classes. So atom will take one class, right? In atoms, we'll talk about those different series, right? Balmer series and all that we have already studied. So Rydberg constant, all those things we will calculate. Energy change. So yeah, those will not take so much of the time. And nuclear and particle physics, we talk about those potentials. So those will not take that much of the time. Right? Nuclear, you have to understand what is binding nuclear, binding energy for nuclear, alpha and beta. So those will not take so much of the time. Okay, these ray optics and wave optics, these are the crucial. Yeah, so we will start and yeah, what where are the other people? If we- Yeah, so I have prepared this question to solve, and then it would be very easy to understand the topics, right? So whatever we have done in interference, let us see that how much do you remember, right? So we have a light of wavelength. Let me, yeah, let me zoom out. So a light of wavelength 600 angstrom is used in Young's double slit experiment. So Young's double slit experiment is for interference, and Young's single slit experiment is for diffraction, right? That we'll see now. So whenever it is given that that is Young's double slit, so we have to remember that that is talking about interference. So separation between slit is 10 millimeters, right? So what is this thing? What they have given? So they have given the small d, that is 10 millimeters, right? Which is 10 into 10 to the power minus 3 meters. So d is given. Separation between double slit and screen is 5 meters. So that is capital D. This is also given. And lambda is also given, right? So lambda is 600. Angstrom is how much? How much is 1 angstrom? Yes, Bhaiya. Angstrom is how much?
10 into minus 1.
Minus 1. So milli is 10 to the power minus 3, right? And then after milli, you have micro. Micro is 10 to the power minus 6. And after micro, you have nano. Nano is how much? 10 to the power minus 9. And then you have this angstrom. So this angstrom is 10 to the power minus 10. Always remember these things, right? These are very crucial. Okay. So this is 10 to the power minus 10 meters. So we know all these things. So separation of second bright fringe from central maxima. So we have this central bright field which is yn equal to 0. And then we want to find out the second bright fringe. So y2 we want to find out, right? This is what we want to find out. So can you tell me what was the nth bright fringe? What was the nth bright fringe? Do you remember? What was the nth bright fringe? What was the nth
Lambda
bright? Yes. Is what you're saying. Lambda.
lambda d by d.
Lambda d by d. This was the width, right? What was go back and check your notes, right? You have those notes. Go back. So bright was a constructive interference, right? So what was that? That was n lambda d by t, right? So if you go back, right? So you had for nth bright fringe, we had this relation. Who got disconnected? Aisha got disconnected. So nth bright fringe was this, right? N lambda and nth dark fringe. This was how much? This was this, right? So we have to remember these things. And the thing that you say, that was the fringe width, right? So that was a fringe. Okay. So this is the nth bright fringe. But we have to find out what? We have to find out the second bright fringe, right? So n is how much? For a second, for second bright fringe, for second bright fringe n is how much? That is 2.
2 lambda d by.
So yeah,
Oh,
so y2 that would be 2 lambda d by d. So everything we know. We know what is lambda, which is 600 into 10 to the power minus 10. We have capital D, which is 5, and then we have this small d, which is 10 into 10 to the power minus 10. Right, so this would be how much? 1 0 we can cancel. So this is 5 2s are 10.
minus 10 minus 3.
Yeah, so this is 6 and 5 2s are 10, and then we have this 0. So we have 10 to the power 2 as well. And then 10 to the power minus 10. And if this 10 to the power minus 3 goes upstairs, so what would be that?
10
What would
raised to 3.
10 raised to 3, right? So then we just see the power. So this is 3 to 5 minus 10. This is 6
Sir,
in, yes.
sir, how did it go like 6 into 10 raised to 2?
How did we get 6 into 10 raised to 2? Oh, yeah. So you see that this is 2 into 60 into 5. So I took 110
Yes.
from here, right? I took 110 from here and then 5 into 2. So 110 from here. So this is 10 to the power 2 and then 1 6. So 6 into 10 to the power. Clear?
Yes, sir. Sir,
Yes.
sir, I'll be back in 1 minute.
Oh, yeah, yeah. Please, yeah, okay. Yeah. Whenever you come back, please give me a sign, right?
Yes, sir, I'm back.
Okay. Yeah. So, yeah. Then what we were doing? So this would be right. This would be 10 to the power. This is 5 minus 10, so minus 5. So this would be the position of the second right foot. Right? Clear?
Yes, sir.
Okay, now let us calculate the second part. So separation of third dark fringe from central maximum. So we know that what is the nth dark fringe? How much is that? So nth dark fringe is 2n minus 1 by 2 lambda d by d. Right, this is the nth dark fringe. But we have to find out what we have to find out the third dark fringe. Third
Y3.
y3. Absolutely right. So this would be 2 into 3
2
minus
into 3 minus 1 by 2.
by 2.
Lambda d by d.
Yeah, lambda d by d. Okay, so who's back? Yeah, Aisha has some problem.
5 lambda d by 2d.
Yeah, so this is 6, yeah, 5 lambda.
Lambda d by 2d.
So now we will put all the values. So lambda was what, 600 into 10 to the power minus 10. D was what? D was 5 meter, I guess. And then 2, and this D was how much? This D was 10 into 10 to the power minus. Okay, so again this 10 goes out, right? This is 2 into 30, right? So this would be how much? 25,
25.
3s are 750. 750 into 10 to the power minus 10 into 10 to the power minus meters. So then this would be how much? 7.5. If I write, let me write 750 first. So 750 into 10 to the power, this is plus minus 7. Then I take two tens from here, so this would be minus 5. Right.
Yes, sir.
So this would be the place of or the separation of the third dark fringe from the central max. Right. Okay. Now we have to find out what is the fringe width. So fringe width is how much? That we know already. 40. Bright and dark both are same. So fringe width, that is beta, and that is lambda d by d. Right? So this is lambda,
Yes,
which
sir.
is 600 minus 10, d is 5, and then this d is this d is 10 into 10 to the power minus 3. So 1 is cancelled. This is 6 5s are 300, 10 to the power minus 10, 10 to the power 3. So this is 300 into 10 to the power minus 7. So 3 into 10 to
3
the power
3.10
minus.
to the power minus 5.
Yeah, so that would be the thing. And lastly, we need to calculate the angular fringe width. Right. So we have calculated that angular fringe width.
Sir,
Yes,
sir, your voice is really low.
my voice is really low. What is that? How it is? What is this clear now? Is this okay?
Yes, sir, I can hear you, but like it's really low. It's not really low, but it's low.
Hello.
Yes, sir, now it's perfect.
Okay, good, good. Thank you. Yeah, so now the angular width. That was theta, and this was how much? That was, I guess, lambda by t, right?
Yes,
So
sir.
this was now what would be this angular orbit? So lambda is 600
600 into 10
minus
raised to minus 10
and then 10 into
by
10.
10 into 10 raised to minus 3.
So 110 cancelled and 60 into. Oh, so okay, yes. Now Aisha, your mic is working. Hello, Aisha. Assalamu alaikum. Yeah. So we are discussing the one of the questions from this wave optics, right? So this would be 60 into 10 to the power minus
6
7. So 6 into 10 to the power minus 6
minus 6.
meters. So this would be the angular fringe.
Width.
Yeah, so this was the question, right? The
Yes.
question, yeah, so the question was why this, yeah, why? Yeah, so the question was that we have a light of, yeah, the question was that we have a light of wavelength 600 angstrom, and that is used in this Young's double slit experiment. And separation between the slits is 10 millimeters. Separation between the double slit and screen is 5 meters. So then we needed to calculate the separation of second bright fringe, separation of third dark fringe width, angular fringe. So these would be the kind of question that we get in your CBC. So please note it down, and if you guys have any question, please okay, please note it down. Yeah, whenever you guys want me to scroll down the screen, please
Sir, we don't need to write the micro, nano, right?
yeah. So that is just for clarification that yes, these are the measurements, right? That is why I have. Yeah, whenever you guys want me to scroll down the screen, please.
Sir, can you please scroll down?
Oh, look this. Yeah, so what it is. Done. Oh, yes. Good, Ash. Okay, you guys please note it down, and then we'll do one question more, and then we'll talk about the last topic, which is the diffractions.
Okay, sir. Done, sir.
Done again. Okay. Aisha, what about you? Noted? Okay, yeah. So then please.
Done.
Done. Okay. Aisha, what about you? Noted. Okay, so now let us do one question more, and yeah, then we will understand this thing. So the question is that in YDSE experiment, a light of having a beam of light, a beam of light consisting of two wavelengths, which is 600 nanometer and 800 nanometer is used. The separation between the slits is 0.28 millimeters, and the separation between the slits and screen, that is how much? That is 1.4 meters. So we have to calculate the least distance, calculate the least calculate the least distance from central maxima or central bright ridge, so that the fringes overlaps, right? So both the fringes are at the same position. So the the question, right? So what do we have? We have a Young's double slit experiment, and in place of a single wavelength, right? In place of a single wavelength, there are two wavelengths. So one is, let's say, one is one wavelength, right? So that is coming here, and that is coming here, right? And the other wavelength is right. So there is another wave. So there is another wavelength which is going there and which is so these are the two wavelengths that we have, and we want to find out the position or the least distance from the central maxima, so that both these bright fringes, right? Both the position of the bright fringes are seen. Okay, so this will have some bright fringe at this place, and this will have some bright fringe at this place. But both these are overlapping means what? We have both, they are equal, right? And they are bright fringes, so they are bright, right? So we have to find out the least distance at which both the fringes overlaps. Is this thing clear, guys? Is this thing clear? So let's say that we will have a central fringe at here, and this will have a central fringe at here, right? So these are overlapping at the center. Now we have to find another distance at which both the fringes are overlapping, right? So both the fringes are overlapping. So this is what we need to find. Is this question clear, guys?
Yes, sir.
Okay. So for let's say we have what is given in the question. Lambda 1 is given, which is 600 nanometers, right? Which is 600 into 10 to the power minus 9 meters. Lambda 2 is also given, which is 800 nanometers, which is 800 into 10 to the power minus 9 millimeters, right? And then the separation between slit is 1.2. So T is given, which is 0.28 millimeters, which is 0.28 10 to the minus 3 meters. And T is also given 1.4 meter. So we have all these conditions, right? And the condition is what? So condition is that wherever, yeah, let me show you from here. So let's say that for one wave, the wave pattern would be this, right? The central one, and then dark one, right? And then bright one, and then dark one. So these would be the wave patterns, right?
Yes, sir.
And let's say this one is for this wavelength, right? So this wavelength and like so we have these ones. But let's say we have another wave, right? Another wave which is coming. So this will have central would be again same. They are overlap. But this one will have a bright fringe, let's say at this place. So bright fringe at this place. So you see that this is different from this one. And this one will have again bright fringe at this place, right? But there would be a least distance at which this one and this one also. So both will have same bright fringe, right? So that is the distance that we want to calculate. So this is the condition. So we know that what is the bright fringe for the one lambda case. What is the bright fringe? Yeah, what is the condition for the bright fringe? Who got disconnected? Oh, Mariam got disconnected. So what is the condition for the bright fringe, Aisha? What is the condition for the bright fringe? This we have done in the previous question. What is the condition for the bright fringe? Yes.
Sir, can you please repeat?
Yeah. So what is the condition for the bright fringe? We have this is the separation from the central maxima, right? So let's say for one wavelength, what is the position of the nth bright fringe? Okay, so let me write it this way, right? So nth bright, or I should write mth bright fringe for lambda 1. This is one wavelength, right? That is ym. So how much would be that? M lambda t by t,
N by
right?
and lambda by
A-
d.
And now let us calculate the nth bright fringe of the other wave, because this is dependent upon the wavelength. So if wavelength is changing, then bright fringe will also change. So nth bright fringe for the other wavelength, right? So that would be yn, and that is n lambda
N
t
lambda
by
t by
t.
d.
So in the question, this is given that their bright fringes overlaps. So the position is overlapping, right? Then what would be, so this is given that ym is yn. So which means that m lambda d by d, this is equal to n lambda 2 d by, right? Which means that this d and this d will cancel, this d and this d will cancel. So we will have m lambda 1 equals to n lambda 2. That would be the case, right? Right? Is this clear, guys? Is this clear, guys? Yes.
Sir, can you hear me?
Yeah, yeah, I can hear you. Is this clear? Yes, I can hear you.
Yes.
So this would be the condition. Now, what is m by n? That would be lambda 2 by lambda 1. So lambda 2 is 800, right? Let me write it as nanometer, because nanometer cancel. And this is 600 nanometers. Nanometer, double zero cancel. This is 3. This is 4. So I will get the position of m as 4n by 3, right? So this would be the position. So if I choose n equal to 1, right? If I choose n equal to 1, then what would be m? If I choose n equal to 1, for
4
n
by
equal,
3.
so m would be 4 by 3. So is this possible? Can the position would be, can this number would be 4 by 3? 4 by third bright fringe. So is this possible? The bright fringes are first bright fringe, second, third, fourth. There are
Yes,
no
sir.
4 by 3, 2 by 3 bright fringes, right? So they are natural
Yes,
numbers.
sir. There is.
Yeah, that m goes from 1 to 1, 2, 3, 4, 5. N goes from 1, 2, 3, 4, 5, right? So the first
Yes, sir.
yeah, the minimum. And in this question, they are saying that the least distance, right? So the minimum would be how much? So that we will have a real natural number. So what should be the first value of n so that we get a real natural number? What would be that? For n equal to 3, right? What would be n? This would be 4 into 3 by 3. So this would be 4. Now this is valid, right? Clear, guys? Is this clear? Is this clear?
Yes, sir.
So now we can say that the third bright fringe of lambda 2 will coincide with the fourth bright fringe of lambda 1, right? So m was for lambda 1. So we can calculate y3, right, for lambda 1. And you guys can check that that would be equal to y4 of lambda 1, right? So y3 of lambda 2, let us calculate that. This would be how much? 3 lambda 2 d by d, right? So this is how much? 3 lambda 2 is 800 and 10 to the power minus 9. D is 1.4 divided by D is how much? This is 0.28. So this goes below, this goes above. So this is 2, right? And then this is 4. So how much would be this? This
Well, 10
is,
and 10, 0 and 400, 0 can be cut, right?
yes,
10,
yes, yes.
0, the 0 of
Yeah,
10 and the
yeah. So
0 of
let us,
400.
yeah, yeah, yeah. So let us cancel, right? So this is how much? 4 threes are 12, 120 into this is 10 to the power 2 and 10 to the power minus 9. So we can write this thing as 120 into 10 to the power minus 7 meters, which is 1.2 into 10 to the power minus 5 meters. So this is the third bright fringe of lambda 2, right? The higher wavelength. And the fourth bright fringe of lambda 1, that would be how much? 4 lambda 1 d by d. So 4 lambda 1 is 600 and 10 to the power minus 9, 1.4 divided by 0.28. And then
28 and
why this 10 came here? So this 10 and then this 100. So this is 2, 110 is cancelled, and this is 2. So then this is how much? 6 to 120 into 10 to the power minus 9 into 10 to the power 2. Same as this one, so we'll get 1.2 into 10 to the power minus 5 meter of lambda 1. So you guys saw that we had this fringes for one case, right? And
yes, sir.
then we had the fringes for the second case. So we saw that this one was overlapping, and the next overlapping came in here, right? So this was for
Yes,
this.
sir.
This was the third one for this one, and fourth one for this blue one, right? So in there we'll get, and this would be the position, separation from the central bank. So is this question clear, guys?
Yes, sir.
Okay, you guys, please note it down, and then we will start. Yeah, so I will do one more topic and then we'll start this diffraction. Please note it down.
So which chapter we're going to start?
No, not the chapter. We will first finish this diffraction part, and then we'll start the model. Right? Maybe structure of atom.
So structure of atom is there?
In atom, yeah, in atom, what do you learn? So learn about Bohr model and all those things, right?
Yes, sir. So can you please scroll down?
Yeah. Yeah, Aisha, you have also.
So can you please scroll a little up?
Oh, guys,
A little.
yeah, is this okay?
Yes, sir.
This is not possible, right? Not possible. So you will have the overlapping for another case also, right? So if you have n equal to how much? N equal to 6, right? Then again you will have the overlapping. But the least one, in the question they have asked this least one. So for least one, n equals to 3 would be the least.
So can
Oh, you want, yeah. Yeah, whenever you guys have noted it down, please So Aisha has noted. What about you? What about you, Maria? Noted.
One,
Okay, yeah. Yeah, whenever you have noted, please tell. Then, okay, good. So now let us understand about, yeah. So there's one topic which is remaining in interference, and that is the sustained. So sustained interference, right? And what is sustained interference, right? So let's say you have two interference patterns, right? So one, this is let's say your bright fringe, and then let's say this is your dark fringe, right? So you see that both are coinciding with each other. Let's say you have one interference like this, and you have a one interference like this, where you have this bright fringe and then this dark fringe. So you can contrastingly say that these are two different. So you can identify both of them are together, right? So the type of interference, when you can see those different, we can identify those bright and dark fringe separately. So those kind of interference are called sustained interference, right? So the type of interference where we can differentiate the bright and dark fringes very clearly, and whose intensity does not vary with time, right? So let's say you have a bulb which is emitting a constant light, and then you have another bulb which is fluctuating, right? So which bulb is a good emitter? The constant one, right? So the intensity that you are getting from a sustained interference, that will not change over time, right? That will remain the same. So those kind of interference are called the sustained interference, right? With time, those kind of interference are called sustained interference, right? And what are the conditions for sustained interference? So saw, you guys just saw from the previous question, right? So yeah, I will talk about them. Yeah, so I will. Okay, first thing for interference is that because the waves are superimposing, right? So for what kind of wave we have taken the superposition? For what kind of waves we have taken the superposition? Or what kind of sources we have considered? Yes. What kind of waves or sources we have considered for the interference? Yes, guys, tell me what kind of sources we have considered. This is the first condition that we talked about. So the sources should be coherent, right? This is the first condition. The sources should be coherent. This thing we have clearly seen, right? The second thing we saw in this example that when we had how many waves in this condition? We had how many waves in this question? We had how many wavelengths? Yes, in this question, how many wavelengths were there? Yes, guys, in this question,
Yeah.
yeah,
Three.
in three, yeah, we had two kinds of wavelengths, right? So the light had two different wavelengths. Then what happened? Then you saw that the interference pattern got mixed up, right? So you got a mixed up interference pattern. But you don't want these kind of interference pattern, right? You want your interference to be sharp, identifiable. Yeah, yes, Aisha, you are correct. So you want your interference pattern to be sharp, differentiable, right? Then you will use a light which has a single wavelength, right, guys? So those kind of lights are called what kind of lights they are called? You have done this in your maybe in your school experiment. You have done this experiment. So what kind of lights are those which have single wavelength? Yes. What kind of?
Sir, can you repeat?
So I'm asking that you require a light which has only single wavelength, right? Because if you have different kinds of wavelength in a single light, then all those interference would be mixed up, right? So to have a sharp and sustained interference, you require a single wavelength of light. So that kind of light is called what? Monochromatic. Yes, absolutely correct. So the sources should be monochromatic. Right? Is this clear, guys? Is this clear? Now the third case. So what is the condition? What is the condition for the what is the condition for the bright and dark fringes? We know that from the central maxima, the distance of the separation, if this separation are large, then we will have a distinct differentiable wave pattern or interference pattern, right? So then this yn should be large. And what is yn? That is, let's say for bright fringe, this is n lambda d by d, right? So this yn is dependent upon d, and this yn is dependent upon 1 by d. Clear? Is this clear, guys? So which thing should be smaller, so that now we want to increase this value. We want to increase this value. So if I want to increase this value, this d is the separation, right? And this d is the separation between the slits. So this thing, if I want to increase this thing, so this thing should be what? Smaller or larger?
Increase.
Increase, right? So which means that the separation between the slits and screen should be larger, right? And the fourth thing that you guys saw, so if I want to increase this thing, so this should be decreased, right? So this should be decreased, and this should be increased. So which means that the separation between the slits and yeah, the separation between the slits should be between the slits should be null, right? And the fourth condition that you require is, let's say that you have this source, and these are, so this is the source, right? And this is your S1, and you are observing this thing here. So this has some lambda, and then this has some t, right? So this should be, so S small s, right? By this capital S, this should be smaller than lambda by 2. So this is the another condition, right? This is the wavelength of this of source, right? This should be S, and this S is the separation between these strips, right? So these distance should be smaller than this wavelength and this separation between the strips. So this is the another condition for the sustained interference. So you guys please note it down, and then I'll start a deflection. So because we have done this interference very extensively, so I will write the results of diffraction directly, right? You guys please note it down, and then we'll start deflection. Please note it down. Yeah, whenever you guys have noted it down. Done. Okay. Yeah. Mayam, what about you? So, what about you? And please note down these things, right? So, this is this small s, and yeah, this is the capital S. So, this small s is the size of the slopes, and this capital S is the separation between the source and the slips, right? And lambda, you know that the wavelength of the light which is coming from this source, d is the separation between the slips. So these are the important parameters. Okay, now I will just write this thing, and then we move on to the deflection part. So the next part is that if you have so interference with white light, right? Interference with white light. And you guys already know that how many wavelength is white light monochromatic or not? Is white light monochromatic?
Yes.
White light is monochromatic. Okay. So we have done this prism experiment, right? If you take this white,
Oh,
yes, now you tell me, is white light monochromatic,
no.
right? So white light,
Splits into 7 colors.
yeah, seven colors. So wave geo, right? Yeah. So one, two, three, four, five, six, seven, right? So the largest wavelength is red, and smallest wavelength is violet, right? So we know that the interference pattern is dependent upon. So let's say you have this white light which is falling. So first you will get a central maxima, right? This would be a white light. This would be a white light, and then you know that how does this bright fringes vary, right? So you know that yn is n lambda d by t. So this is dependent upon lambda. So the first pattern you will get will have a small wavelength, right? So first fringe that you will get would be of what? Violet or red? Yes. What would be the
Violet.
violet, right? So then this would be violet, and then you will get indigo, right? And then you will get all these patterns. So these would be the kinds of pattern that you will get in the case of the white light. So just remember this, right? So you'll get the central would be white light, then violet, and then VPO, right? So yeah, these experiments, when you go to your graduation class, then you guys will do these experiments. These are very beautiful experience, right? So you guys will get some slits and some white light and some monochromatic light, and then you will see these colorful parallel lines. These are very lights. Did you guys do you have done this experiment in your school? Did you guys do this interference or diffraction pattern in your school in practical?
No, sir.
Okay, maybe in graduation, guys. Uh, Yeah. So now let us start right diffraction. I guess in next class. Yeah, but before I do that, you guys please note down this part. You guys can put it down. So please note it down, and then we will talk about diffraction. Quickly note it down. Yeah, noted, guys.
Sir,
Yes,
so can you hear me?
yes, yes, I can hear you. Yes, yes, I can hear you. Yes. Can you guys hear me? Aisha, can you hear me? I guess Mariam cannot hear. So, yes, guys.
No, sir, I can hear you.
Yeah. So, you want to ask something?
No, sir, I said done, sir.
Oh, done. Okay, yeah. Then let us start this diffraction, right? Okay, so precisely we will talk about the diffraction of lights, right? So this is a very beautiful example to talk about diffraction. So we have diffraction in sound waves, we have diffraction in electromagnetic waves. Yeah, so light is also an electromagnetic wave, and then we have diffraction in other kinds of waves as well. What is diffraction, right? So let's say that you have this wall which is sound, right? So this wall is sound, okay, and you are, let's say, the person is shouting from here, right? Not but let's say from right. So his voice will go, and then his voice will be heard to this person, right? So you see that this person is speaking in here. So the waves are going in this direction, in this direction. But these sound waves are also bending, right? Bending, and it is reaching here. Here. So the bending of waves are called diffraction. So these kind of situation of the sound waves we see in our daily life, right? But in our daily life, do we see light? So let's say you have a wall, and then behind that wall, the bulb is glowing. So can you see the glowing of that bulb from behind? You cannot, right? You cannot see
Sir,
that.
can you please repeat?
Yeah. So let's say let's say that if this person is shouting, right, and the sound waves are traveling. But it may also happen that the sound waves are traveling and they are bending and they are reaching this person, right? So this happens, right? Let's say that the person is standing here. So he or she can hear his voice in this direction. So
Yes, sir.
the sound waves are going and they are bending. They are bending and reaching here, right? But let's say if you throw some light in here, right? So will the light will reach this person?
No.
No, right? Because the light is not bent. But for the case of sound waves, right? For the case of sound waves, what did we see? We can hear this person from this in front of the person,
Depends.
right? Because sound waves are bending. So sound waves are showing this diffraction pattern in our daily life, right? In our daily life, we are seeing this diffraction pattern. this is happening. This is happening because the condition of diffraction is that the wavelength of this, whatever the waves are propagating, right? So this lambda should be should be comparable to the object, right? So the so the lambda of the sound wave is in the range of let's say micro or milli, right? So it is ranging from 10 to the power t to 10 to the power minus 6. So this is the wavelength of sound waves, right? So this is the wavelength of sound waves,
Yes.
but the wavelength of visible light. What is the wavelength of the visible light? Light wavelength is starting from 400 nanometer to 700 nanometer, right? So this is in 10 to the power minus 7. And this is also true, right? This is like it's 10 to the power minus 5 and so on. So that is why we can have the objects which are in the micro range. So for those kind of objects, we can see the diffraction pattern of sound, right? So diffraction of sound we see clearly, but the wavelength of light is 10 to the power minus 7 meter, right? So in our daily life, what is the size of the objects in our daily life? That is in micro range, right? Milli and micro range. So in this range, the objects are there, right?
Yes, sir.
That is why the
Yes, sir.
yeah the object size is 10 to the power minus 3, or let's say minus 5. So that is why this is bigger than the wavelength of the light. So that is why in our daily life we don't see these kind of diffraction pattern in our daily life, right? So diffraction of light we don't see in our daily life. But what do we do is that we make a simple, right? We make a simple blade. So this is a blade, right? Blade has this very thin, very thin, sharp edges, right? So those sharp edges are very small, right? So for those kind of sharp edges, we will see that the lights are bent, right? So we will see the light not in here, we will see the light in here, right? But let's say if we have different lights, so then they will superimpose and then they will make a pattern, right? So the diffraction of light is what? Is the bending of light through a very comparable object, right? So diffraction of light
Yes,
through an
sir.
object which is very small, and the wavelength of that object is comparable to this edge that is from where the light is going. So this is the idea of diffraction. Okay. So let us write the definition. So bending of light, bending of light, an object whose size is comparable to the wavelength of the incoming light. So this is a very crucial condition. The size of the object should be comparable to this bending of light. Because in our daily life, we see the reflection, we see the diffraction, but we don't see this diffraction, right? So that is because the size of the objects in our daily life is not comparable to the wavelength of the light. So that is why we don't see this deflection in our daily life. So that is the definition of diffraction. But how many kinds of diffraction do we have? So there are two kinds of deflection. One is called the Fresnel deflection, and the other one is Fraunhofer. Yeah. So are you in the garden or something, Maria?
No, sir. They're my birds.
Oh, those are your birds. Yeah. So
Sorry, sir.
no, why? So that is totally fine. That is totally fine. So I just asked for curiosity, right? Don't bother about that. So what is the Fresnel diffraction? So let's say you have a source, right? And then you have some slit. So if the slit and the source, so the separation between the slit and the source is finite. So when the separation